Welcome, learner, to another deep dive. Today, we're plunging into a topic that often flies under the radar but is absolutely critical for our energy future: global heat demand. You might think of electricity or transport when we talk energy transitions, but, well, as you'll discover, heat is a massive piece of the puzzle, often overlooked, really. We've got a fantastic source document to guide us today. It's a really comprehensive study titled Global Local Heat Demand Development for the Energy Transition Timeframe up to 2050. It gives an incredibly detailed look at how our world's need for heat is evolving. From your morning shower right up to the biggest industrial plants making steel or chemicals.
Yeah, and what's truly fascinating here, I think, is that even though heat is such a huge part of how we use energy, getting good detailed data has been surprisingly tough, globally, I mean. This study, though, it really steps up. It fills that gap by providing this granular database of heat demand across 145 mesoscale regions worldwide. These are like detailed subnational areas, and it projects all the way out to 2050.
So what's our mission today? Well, we're going to unpack the current state of global heat demand. We'll explore the projections for different kinds of heat, understand the really big regional differences that are emerging, and even peek into the hourly heat demand profiles. Those are super important for future energy systems. You'll definitely walk away with a much clearer picture of how our homes and industries will be heating up or maybe cooling down in the next few decades, and why it matters so much for climate goals. All right, let's dive straight in. First, just the sheer scale of this. Heat's influence on our energy landscape. The findings are quite striking. In 2018, heat consumption accounted for a staggering 50% of global final energy consumption.
50%.
Yeah, compare that to transport at 29% and power at 21%. And get this, it was responsible for 40% of global CO2 emissions.
Wow.
That percentage, it really just underscores how urgent it is to tackle heat in the energy transition.
It really does. And this study breaks it down in a very insightful way. Globally, about half of all that heat consumption, it comes from industrial processes.
Okay, so manufacturing, agriculture, that sort of thing.
Exactly. Everything from making cement to food processing. The other half is largely stuff we're all familiar with: heating our homes, heating water, cooking.
Yeah.
Just to give it more context, like if you look at the EU, almost half of its total final energy use is for heating and cooling.
Right.
And over half of that is residential homes. About a fifth is industry there. So it's a huge slice of the energy pie, pretty much everywhere you look.
Okay, this next part gets really interesting. Projections. This study predicts that total global heat demand will actually increase from about 45,400 terawatt hours thermal TWatt, that's the unit in 2012, up to roughly 56,600 TWatt off by 2050.
So an increase overall.
Yes, but it's not just a straightforward climb. There's some fascinating, pretty complex things happening across four key heat types they looked at. There's industrial heat demand, or IHD, domestic hot water, DHW, space heating demand, SHD,
Yeah.
and biomass for cooking, BCH.
Which naturally leads to the question, what's actually driving these changes? Why the increase and why the shifts between those types? Well, for IHD, industrial heat demand, it's mainly global economic development, especially the rapid industrialization happening in emerging economies.
Okay.
For DHW, domestic hot water, that's pretty directly linked to rising standards of living, better access to modern stuff.
Right.
SHD, space heating, that's influenced by a mix. Building efficiency measures play a huge role, but also, interestingly, the impacts of climate change.
And the last one, BCH, biomass for cooking.
Ah, yes. For BCH, the research shows a really crucial phase-out happening, basically moving away from traditional biomass like wood fires for cooking, and that's driven by really important health and environmental reasons.
Let's dig into those types a bit more because the way their shares change tells a big story. Back in 2012, IHD and SHD were almost neck and neck. Each was over 41% of total global heat demand.
Roughly equal shares.
Yeah. BCH, the cooking biomass, was about 13%, and DHW hot water was the smallest slice at around 3.3%.
But fast forward to 2050 in the projections, and things look quite different. There's a significant rebalancing. Industrial heat demand, IHD, is expected to become the dominant force, making up nearly 55% of total heat demand by then.
Wow, that's a big jump to 55%.
It is. And it's fueled by that substantial industrial growth we mentioned, particularly concentrated in places like sub-Saharan Africa and South Asia.
Okay, and what about biomass for cooking? You said that was phasing out. It started at 13%.
Yeah, it was quite significant.
Uh-huh.
But the projections here are really stark. BCH is expected to be almost completely phased out, dropping to like 0.0001% by 2050. Basically negligible.
That's
Well,
incredible.
it really is. And it represents such a critical transition. Moving away from traditional biomass for cooking has these massive health benefits, cutting down indoor air pollution, which is a huge issue.
Right.
And huge environmental benefits too,
Yeah.
less deforestation, lower emissions. It's a massive positive shift.
So, okay, BCH almost gone, IHD way up. What about the others? We're seeing domestic hot water, DHW, more than double its share to 6.2%, which, as you said, reflects those rising living standards.
Exactly.
And space heating demand, SHD, while it's still a big chunk, it's projected to actually decrease its overall share, down to about 39% by 2050, which seems a bit counterintuitive with population growth.
It does seem that way at first glance, yeah. But that decrease in SHD share, it's really a powerful testament to how effective energy efficiency measures in buildings can be. The analysis suggests these improvements are so impactful, they actually lead to global space heating demand peaking around 2035.
Peaking, so it goes down after that.
Yes, after 2035, it starts a steady decline, even with growing populations in some areas. Climate change also plays a role, a noticeable one, in reducing SHD, but it's smaller than the efficiency effect, just to put a number on it. The study calculates that without those building efficiency improvements, SHD in 2050 would be something like 6,754 T-whites higher.
Wow.
Yeah, it really shows the strong impact of investing in efficiency.
Okay, this study doesn't just do global numbers, right? You mentioned 145 regions, so let's travel around the world a bit, see how these trends play out differently.
Definitely. The regional variation is key. So if we take space heating demand, SHE for example, in Europe we see demand continuously going down. That's partly due to falling populations in many countries, plus those efficiency gains really kicking in.
Okay, declining in Europe.
But contrast that with Northeast Asia. There, SHD is projected to continuously increase, even though China's population is expected to decline after 2035.
How does that work?
It's a fascinating catch-up effect. The study suggests that the current relatively low per capita space heating demand in China will rise towards the sort of global average trend line, and that effect actually outweighs the population decline and the efficiency improvements there.
Huh. Interesting. Shows how local development paths really matter.
Absolutely. It's a great illustration of that.
Okay, what about domestic hot water, DHW? Where are the biggest shifts happening for, hot showers and washing up?
Well, the biggest growth drivers for DHW are really concentrated in sub-Saharan Africa, South Asia, and Southeast Asia. Sub-Saharan Africa, for instance, is projected to see its DHW demand increase more than sixfold by 2050.
Sixfold.
Yeah. It's this combination of economic development, boosting living standards, and of course strong population growth in the region. But interestingly, Eurasia, especially Russia, is projected to see a decrease in DHW demand.
A decrease. Why?
It seems their starting point, their per capita consumption, was initially quite high, maybe above the sort of global average. So the projection shows it aligning more with global trends, plus they expect population decline.
Right, that makes sense. Okay, and IHD, industrial heat. Where's the industrial engine really firing up?
Sub-Saharan Africa stands out again, massively. The highest projected increase in IHD. Get this, 1,208% of its 2012 value by 2050.
1,200%.
Yeah.
That's almost hard to picture.
It is. It reflects this anticipated major industrialization process, basically building up a huge amount of industry over the next few decades. South Asia is also expected to increase its IHD more than 4 times over. Huge growth there, too.
And the established industrial regions.
Well, Europe and North America actually show a negative trend for IHD. Their demand in 2050 is projected to be lower than in 2012, about 85% for Europe, 91% for North America.
So efficiency and maybe some deindustrialization or shifting industries.
Exactly. Driven by efficiency measures, structural changes in the economy, and population factors in those already industrialized nations.
And that phase out of biomass for cooking, BCH, where is that transition most concentrated?
It's primarily in the global south.
Hmm.
Sub-Saharan Africa, South Asia, Southeast Asia, that's where most traditional biomass cooking happens now. The study notes a moderate reduction between 2012 and 2020, especially in Sub-Saharan Africa, but it was somewhat offset by fast-growing populations. But the projection shows a much faster reduction after 2030. The idea is that most BCH will be substituted by clean cooking technologies like LPG, electricity, improved cook stoves by 2050, which is, as we said, a profound shift for daily life there.
Right. Okay, now this study goes even deeper, you said. It provides hourly heat demand profiles for all these regions. Why is that level of detail, that granularity, so important? It seems like a ton of data.
It's absolutely critical.
Mhm.
especially for planning and modeling our future energy systems, particularly as we bring in more renewables.
How so?
Well, knowing when heat is needed during the day or across seasons, not just the annual total, is essential for optimizing energy supply. Renewables like solar and wind are variable, right? So you need to match supply and demand much more carefully. Take space heating profiles, they vary hugely. In Finland, you get these long, strong peaks in winter demand. But even in summer, you might get cold snaps needing some heating. But then you look at somewhere like equatorial Indonesia. They need space heating year-round because of humidity control or specific building needs, but it's at a very low, pretty constant level. Totally different pattern.
Requiring different solutions, I imagine.
Exactly. It shows heat demand isn't just a flat line.
And domestic hot water,
Yeah.
DHW. I guess those patterns are maybe more consistent globally. People showering, cooking.
Broadly, yes.
Yeah.
You do see pretty consistent patterns. DHW demand is generally concentrated in the evening hours, people getting home, bathing, cooking. But the study also shows how seasonality affects it. Regions with bigger temperature swings between seasons show more variation in DHW demand, maybe more hot water use in colder months, for instance.
Makes sense. And industrial heat. I think many people assume that's just a constant base load, factories running 24/7.
Yeah, that's a common assumption, but it's not the whole picture. The IHD profiles in the study show a clear baseload component, that's true, but they also show significant ramping up in the morning hours, typically between 6 and 8 a.m., as day shifts start, machinery powers up.
Huh.
And seasonality affects industry too. In Finland, again, you can clearly see reduced process heat demand during the few warmer summer months, maybe maintenance shutdowns, or just less need for heating inputs. So industrial heat isn't just constant, it has its own rhythm, influenced by climate, by working schedules. The study even calculates a baseload ratio for IHD.
Oh, what's that?
It basically shows the share of demand that is truly 2047 versus the share that fluctuates daily or seasonally. For 2020, it ranged from about 76% to 96% across regions. So a big chunk is baseload, but there's definitely a dynamic part too.
Okay, so we've covered a lot of ground. The scale, the different types of heat, the regional variations, even the hourly patterns. What does this all mean when we sort of zoom out? How does it fit into the bigger picture of other energy transition studies?
Well, this is where it gets really interesting and maybe a bit challenging for planners. This study's projection for total heat demand in 2050, remember, around 56,600 Thai wheats. That's actually quite a bit higher than what many other studies project.
Higher. How much higher?
Significantly. The average of other studies reviewed in the paper is much lower, somewhere around 42,000 to 43,000 TWatts.
Wow, that's a massive difference, like 14,000 to what the difference.
Exactly. It highlights that there's actually a pretty significant lack of consensus in the literature about where future heat demand is heading. And this isn't just, an academic point. For people making policy or investment decisions, knowing that the models disagree so much is really important.
Yeah, because how do you plan if the forecasts vary that wildly? What drives such a big spread?
It really boils down to the underlying assumptions. Different studies make widely diverging assumptions about key factors, things like how much overall efficiency improves, how standards of living evolve, the trajectory of economic development, especially industrial growth. This particular study tried to be very comprehensive, explicitly considering population growth, economic development measured by GDP and industry value added, specific annual efficiency improvement rates for industry and buildings, cook stove efficiency improvements, even temperature changes from climate change.
That sounds like a huge number of variables to juggle.
It is incredibly complex, and it means that strategies for decarbonizing heat, which is essential, need to be really robust and flexible. You can't just bet on one single forecast when there's this much uncertainty.
Right, you could end up overbuilding or underbuilding infrastructure.
Precisely. It really puts a premium on adaptable, maybe more modular solutions.
And given that initial scarcity of data you mentioned, how confident can we be in these kinds of detailed projections? How do they validate this?
That's a fair question. And validation is definitely tricky. As we said, a key reason for doing this study was the lack of comprehensive national heat data to begin with. They did compare their results where possible. For the EU, they found pretty good agreement for space heating and domestic hot water compared to existing EU-level data. So that builds some confidence.
Okay.
However, they also noted their model tended to slightly overestimate industrial heat demand in some specific areas, suggesting that getting even more detailed data on the structure of industry in different regions is still needed to refine the models further.
So it's an ongoing process. Better data leads to better models.
Exactly. It's a continuous loop of improvement. But this study represents a really significant step forward in mapping out that demand globally and regionally.
Well, that brings us to the end of our deep dive into global local heat demand development for the energy transition timeframe up to 2050. It's abundantly clear that the heat sector really is this sleeping giant in the energy transition, isn't it? It absolutely demands our attention if we're serious about effective climate change mitigation.
Absolutely. Understanding these complex global and local heat dynamics, all the regional variations, the hourly profiles, it's just crucial for finding the best, most sustainable ways to provide that heat. Because the future of heat supply, which today is still so heavily reliant on fossil fuels, it just needs a radical and a well-informed transformation.
So, as you, our listener, reflect on all this, here's a final provocative thought for you. If our understanding of something as fundamental as global heat demand still shows such wide variations in projections and clear areas where we need better data and modeling, well, what other hidden, maybe systemic energy challenges might be out there, just waiting for their own deep dive to unlock their secrets and properly guide us towards a truly sustainable future?